Let's look at some applications of functions and how to interpret functional statements. First example, let's say the function y equals f of x gives the number of gallons of paint needed to paint an area of x square feet. Let's interpret the statement f of 10,000 equals 40. To interpret this, we want to think about where the 10,000 and the 40 is. 10,000 is inside the parentheses, so if you think about what's inside the parentheses in our definition, that would be x. What does x mean in this problem? If we read through it again, the x is talking about square feet, specifically the area in square feet. So this is 10,000 square feet of area. The output, 40, or the number 40, comes after f of 10,000. It's what f of 10,000 is equal to. So 40 would be like the y value. And the function y equals f of x, y gives the number of gallons of paint. So this would be the gallons of paint needed to paint this area of 10,000 square feet. So putting that all together, if we know that 40 is the gallons of paint needed to paint 10,000 square feet, just write that in a sentence. You can describe either of those numbers first, but you need to connect them. So, to paint an area of 10,000 square feet, you need 40 gallons of paint. Again, you could say 40 gallons of paint will cover 10,000 square feet of area. That would be another proper way of saying this. The main thing is you need to connect these two numbers with what they represent in the application when you interpret a functional statement. In our next example, we actually have an equation to go with the description of our function. A company's profit can be modeled by the function P of t equals t squared minus 6t plus 17, where the profit in thousands of dollars for the year that is t years since 2005. Let's find and interpret P of 3 first. P of 3 can be found by plugging the 3 in wherever you see t, because 3 is in the t position. So 3 quantity squared minus 6 times 3 plus 17. This is an application, so you could use a calculator. It's not too bad to do. 3 squared is 9, minus 18 is negative 9, plus 17 is, I think, 8. So what we have here, P of 3 equals 8. If we want to interpret this, so that's the next thing we need to do. We need to think about what 3 is and what 8 is. The 3 is t, and that's the years since 2005. Well, for 3 years since 2005, we are in 2008. And then remember, the function is calculating profit, and it's profit in thousands of dollars. So the company in 2008 has made $8,000. So, and I should say that's in profit. So that's finding P of 3 and then interpreting it. The next question says, determine when the profit gained by the company was $24,000. Show your work and give your answer in a sentence. So, if the profit was $24,000, this is the output of my function. Now remember, my profit is in thousands, so if I wanted to say P here of something equals the profit, I wouldn't say 24,000 with the 3 zeros, I would just say 24. So let's go ahead and write our equation out. T squared minus 6t plus 17 equals 24. So when, I need to find the time. So we're going to solve for t in this equation. This is a quadratic equation because of the t squared, so we're going to subtract the 24 from both sides. 17 minus 24 would be negative 7. Factor the trinomial you have on the other side into two binomials, t times t. I think we're going to use a -7 and a +1 will give us a -6 in the middle. So I get two factors that I can set equal to 0. T minus 7 equals 0, or t plus 1 equals 0. T minus 7 equals 0 is going to result in a solution of t equals 7, and then the other solution will be -1. Now, both of these are true solutions for the equation, but in this scenario, we're talking about years since 2005. We're talking about going forward in time, not backward in time. So we do not consider negative time. We don't consider going backward in time, only going forward in time. So 7 years after 2005, we'd be in 2012. The company earned $24,000 in profit. So you could then check that by plugging, for instance, 7 back into the equation. So if I were to take the p of 7 and throw it in, 7 squared minus 6 times 7 plus 17, this would be 49 minus 42 plus 17 would give me 7 plus 17, which is 24, which is exactly the profit that I wanted. Sometimes you won't be given an equation for a function. Instead, it'll be described, and you'll need to create the equation yourself. When you do that, you'll need to define the input variables as well. We can pay attention to how the wording exists in the description of the function to identify the input and output variables for that function. In our first example, the monthly electric bill in dollars as a function of the number of kilowatt hours, where 6 cents per kilowatt hour is charged in addition to a monthly fee of $6.50. What we have here first described is the monthly electric bill in dollars. Notice it says as a function of the number of kilowatt hours. So as is kind of like saying is. So what we have here is the bill is being described as a function of the number of kilowatt hours. So I'll just say kH for kilowatt hours that are used. So the input, one hint is that whenever you see as a function of something, that prepositional phrase of is going to be describing the input. And what we started with, the electric bill, is the description of the output. So what we want to do is create an equation for this bill. Because we're talking about a bill, we could use B for the function name, but you could also use F like I did here, the name of the function. It would be really your choice. So what we have is a name of a function that is calculating the bill. We often use X for the input, but if I'm going to use X, then I want to make sure I define X as the number of kilowatt hours. So let X be the number of kilowatt hours that are used. And what I'm going to then do is create an equation described in this particular problem. 6 cents is charged for each kilowatt hour in addition to a monthly fee of $6.50. So I can write that in an equation by saying 6 cents for every X kilowatt hours plus a monthly fee in addition means plus a monthly fee of $6.50. A lot of times people will start with $6.50 because that is what happens automatically. Plus, again, 6 cents. Now, since this was in dollars, the $6.50, I should write the cents as dollars. So 0.06 for every kilowatt hour means I'm multiplying by X. So this is an equation that will give me the electric bill for the month. And it's written in function notation based on the wording in the problem. In our second example, we're talking about the total cost of downhill skiing for a season. So we're talking about the cost as a function of the number of times you go. So the input is the number of times you go. So there's my input, and my output is my cost. So I want to create an equation for this scenario. My input, I'm going to call it x again, but you could use a different variable. And we're going to define that x. We're going to say let x be the number of times you go. Now to create the equation, I need to read further. It says that season, the number of times you go that season, given that you purchase a $500 season pass. Now think about how passes work. You purchase it once, in this case for $500, and it allows you to do what? It allows you to go 1 time, 2 times, 3 times, 4 times, as many times as you want during that season. So how much are you really paying? You have to pay $500. Does it matter how many times you go? No. It's a better deal if you go a whole bunch of times, but you're only paying $500 once. So this is a flat fee. F of x is equal to 500. So even though our input is x, and x is the number of times you go, in the function, f of x is equal to a flat fee of $500. So the function actually is what we would call a constant function, because it is representing the fact that you pay $500 once and that's it. It's a constant price. So we call this a constant function. If you were to graph this function, you would see that it is a horizontal line. So a horizontal line is always when you have an output equal to a particular constant value.